So, let's talk about supercomputers. We're going to peel back the layers on these incredible machines. Machines with computational power that is so massive, it's almost hard to wrap your head around. They're literally designed to solve humanity's biggest, most complex problems. To really get this, let's start with a wild fact. The smartphone that's probably in your pocket right now, it has about the same processing power as a top-of-the-line supercomputer from the mid-1990s. A machine that was busy running nuclear simulations. That's a staggering leap in technology, right? So if your phone is basically a vintage supercar, what does that make the machines we call super today? Okay, so what is the real difference here? It's not just about being faster. It's about having a totally different job. Your personal computer, your laptop, it's a master of multitasking. It juggles dozens of small jobs one after another sequentially. But a supercomputer, it's built for one thing and one thing only, to tackle a single, colossal problem by throwing a whole army of processors at it, all working on different parts at the exact same time. That's what we call parallel processing. And that really gets us to the core of what a supercomputer is. It earns that super title by linking up a massive number of processors into one single cohesive system. It takes a gigantic computational problem, shatters it into millions of smaller pieces, and then hands each one of those pieces to a different processor. They all work in parallel, like a perfectly synchronized orchestra, to come up with one single unified answer. So, how in the world do you build these digital armies? I mean, to really get what makes these machines tick, we've got to look under the hood, and we have to talk about how we even measure this kind of mind-boggling power. The key metric we use is something called FLOPS. That stands for floating point operations per second. Here's a good way to think about it. If your laptop's performance is kind of like its gas mileage in the city, FLOPS are a supercomputer's absolute top speed on a Formula One racetrack. It measures how many really complex math calculations, the kind you need for science and engineering, a machine can crank out in just 1 second. And the secret to that speed isn't one giant engine, it's millions of them all working together. And what's really amazing here is just the sheer scale we're talking about. We've gone from thousands of operations per second, kiloflops, to billions with gigaflops. That's kind of where your gaming console hangs out. But supercomputers, they operate way up in the realm of petaflops. That's quadrillions, and now exaflops. That's quintillions of calculations every single second. A quintillion is a one with 18 zeros after it. Just think about that. So how do you get to those insane flops numbers? It all comes back to that core strategy, parallel processing. You take a massive problem, say modeling the entire Earth's climate. You break it down into countless smaller calculations. Each of those tiny bits is sent to its own processor, and they all solve their piece of the puzzle at the exact same time. Then, at the end, all those individual answers are put back together into one giant, comprehensive solution. That's how you get to quintillions of operations a second. And, when we say thousands of processors, we're really underselling it. The current world champion, the Frontier supercomputer, has over 8.7 million processor cores. To put that into perspective, your fancy new laptop might have, 8 or 16 cores? Frontier has millions, all working in perfect harmony. And of course, to manage all that processing, you need a ridiculous amount of memory. Frontier's working with around 9.2 petabytes of RAM. A single petabyte is 1,000 terabytes. We're talking about hardware on a scale that is it's almost beyond imagination. So the big question is, what do we actually do with all this power? I mean, what's the point? Well, this is where supercomputers stop being just technological marvels and become these indispensable tools for science, for progress. Basically, they act as our digital crystal ball. And this quote from Turing Award winner Jack Dongarra just perfectly illustrates their main purpose, simulating reality. He says, instead of doing these expensive, time-consuming physical experiments, like actually crashing a real car into a wall, we can now build a perfect digital model of that car and run thousands of virtual crash tests to find weak spots and build safer vehicles. And this ability to simulate reality gets applied to our absolute biggest challenges. We use supercomputers to make more accurate weather forecasts and model long-term climate change. They help us discover new drugs by simulating how molecules might interact. They even let astrophysicists model the collision of entire galaxies. They are absolutely critical for everything from finding new energy sources to developing clean power, like nuclear fusion. Now, with this kind of world-changing capability on the line, it should come as no surprise that it has kicked off a fierce global competition. And this isn't just about bragging rights. The nation with the fastest supercomputer has a massive edge in economic innovation, like designing new medicines or materials, and in national security, from cryptography to defense. It's truly a strategic race, and it's pushing us into a whole new era of performance. And if you look at the current leaderboard, the field is pretty dominated by a few heavyweights. The top 3 machines, El Capitan, Frontier, and Aurora, all in the United States, have each smashed through that 1,000 petaflops barrier. That's a pretty clear lead in today's global race. So what's really crucial here is that these top machines have brought us into a brand new era, the age of exascale computing. An exascale system is any machine that can perform at least 1 exaflop, which, remember, is 1 quintillion calculations every second. This is the next great frontier, and we are there. A quintillion is a number so big, it's just really hard for our brains to process. So let's try an analogy. Imagine you gave every single person on Earth a calculator and told them to start crunching numbers nonstop. It would take the entire population of our planet over 4 years to do the math that an exascale machine like Frontier can do in just 1 second. So where do we go from here? Well, looking ahead, all of this immense power is starting to merge with another game-changing technology. And it's creating a combination that promises to speed up discovery at a rate we've just never seen before.
And that technology is, of course, artificial intelligence. Supercomputers are the perfect engine for training today's gigantic AI models. You know, the large language models that are changing everything. They need this level of power for their huge datasets and complex algorithms. And in turn, AI is helping scientists make sense of the mountains of data that supercomputer simulations create. It's this incredibly powerful, symbiotic relationship. And that leaves us with a final, pretty awe-inspiring question. We now have tools that can simulate the universe, design life-saving drugs, and predict the future of our climate. With the ability to perform a quintillion calculations every single second, the only real limit seems to be the scope of our ambition. So what great challenge should we point this incredible power at next?